I am Saifullah Al-Mamun. Today I present cutting tool technology. Total content for tool life, tool material, tool geometry, cutting fluids.
Saifullah, can you make full screen? Can you make your presentation full screen? Yep, good.
For content, first two tool material and tool geometry I present, and other tool geometry and also cutting fluids presents other partner. Machining operation can't imagine without cutting tools. The cutting tools, high force and temperature gradient. Cutting tool technology has two basic principles: tool geometry and tool materials. Tool life. There are three types of failure of tools. First of all, it's a fracture failure. This occurs when the cutting speed excessive. Temperature failures. When the temperature is too high, then the top point of cutting becomes warmer and melting, and that's why the cutting tool wire fracture. That's why cutting tool melted. As a result, there is a wire and gradual wire. Gradual wear of the cutting edge causes loss of tool shapes, reduction in cutting efficiency, and acceleration of wearing as the tool becomes heavily worn. This type of gradual wear is highly required for cutting tool technology than the other two fractures. There is tool wiring, gradual failure of tool wiring. Gradual wire occurs at two principal locations on the cutting tool, at the top rake face and other is flanks. There are four types of wires: flank wires at the edge of the cutting surface, and crater wire is the top surface. Crater wire also known as cavity wire. Checking of the cutting tools indicated in the picture. Notch wire means chipping on the cutting edge, and it's a nose radius wire means nose wire. Picture A, there is a crater wire, and other picture flank wire. Tool life. The duration, the tool performed as a cutter, the time known as tool life. There is a figure to cut time of cutting versus tool flank wire. It can be tool rack wire, cracker wire also characterize the same figure. At the initial stage, break in period, initial stage, tool wire is high. After some period, the tool wire is linear. Then after some time, sometimes of operation, that failure region occurs, and there is a break of tool. Tool life versus cutting speed is shown in the figure. Cutting is in the figure we can see the higher the cutting speed, that if the cutting speed is very high shown in figure 1, then the tool wire is very high. And cutting speed gradually, if the cutting speed gradually decrease, then tool time of tool wear also decreases. In 19th century, Taylor uh, derives the equation, the relation known as Taylor's tool life equation, that is V to the power n equal to C, where V is a cutting speed, T is tool life, and N and C are parameters that depends on feed, depth of cut, work material, tooling material, and the tool life of criteria. Tool life criteria in practical operation: complete failure of cutting edge, virtual inspection of flank by the machine operator, fingernail test across cutting edge, change in sounds emitted from operation that can be observed by the operator, chips become robbing, steering difficult to dispose of, degeneration of surface finish that can be observed by the operator, increased powder in the cutting surface, workpiece count, and cumulative cutting time. This is similar to the previous workpiece count, except that the length of the time the tool has been cutting is monitored. There is a chart where the values high steel, non-steel, steel work, cement and carbide, and ceramics shown the values of N. Where the values of N and C is lower, then the wire is also high, then and the values of N and C higher, the wire also very uh, smaller amount. Tool material, there are three important things: toughness, that to avoid failure, the tool material must possess high toughness. Toughness is the capacity of material to absorb energy without failing. Hot hardness, hot hardness is the ability of a material to retain its hardness at high temperature. This is required because of high temperature environment in which tool operates. Another is wire resistance. Hardness in the single most important property needed to resist abrasive wire. All cutting tool material must be hard. However, we resist in material cutting depends on more than just tool hardness because of the other tool wire mechanism. Cutting tool materials. There are different type cutting tool material that can be used in the 17th century to present. At the initial stage, plain carbon and low alloy steel are used. Then high speed steel, cemented carbides, garments and coated carbides, ceramics and synthetic diamond, and cubic bronze nitride are used. In those type, high high speed steel and cemented carbide and diamonds are 90% used in tooling operation in different factory. There is a curve that shows hardness versus temperature. Typical hot hardness relationship for selected tool materials: plain carbon steel shows a rapid loss of hardness as temperature increases. High speed steel is substantially better, while cemented carbide are significantly harder and elevated temperature. This curve shows that when temperature goes high in the tooling surface, then the hardness become uh, uh, harder material becomes softer. In these cases, cemented carbide and ceramics are better for selecting the cutting tools. Tool materials: plain carbon and low alloy steel that are used in 17th century. Before high speed steel are invented. Due to a high carbon content and heat treated, its hardness is poor. That's why wire is also high. Then high speed steel. High steel it contains tungsten type and molybdenum type, two types. Tungsten type 12% to 20% of tungsten, and molybdenum type 6% tungsten and 5% molybdenum. Other elements: tungsten, molybdenum, chromium, vanadium, carbon, cobalt, and other some grades. Typical composition of high speed steel: tungsten 18%, titanium 18%, tungsten 4%, chromium 1%, vanadium and also 0.9% carbon. High speed steel used extensively for complex geometry such as drill, heat treatment. Red RC is a constant value is 65. Regrinded for reuse. It can be reused. High speed steel of the cutting tools can be worn or wire. Then it can be reused for regrinded. There is a thin coated on the cutting tool surface. Cast cobalt alloys. Its composition: 40 to 50% cobalt, 25 to 30% tungsten, and 15 to 20 other percent. Casting in a graphite mold and grind. Toughness is not as good as high speed steel. Hot hardness is better. This is a low use in industrial level cast cobalt alloys. Cemented carbides. Cemented carbides, carments, and coated carbides. There are some advantages of this type cutting tools: high compressive strength and modulus, high room and hot hardness, good wear resistance, high thermal conductivity, low in toughness, then high speed steel. There are different type of grades of cemented carbides. Non-steel grade, that is tungsten carbide cobalt. Steel grade, titanium carbide, tantalum carbide. Due to high solubility of tungsten carbide steel, resulting in extensive crater wire. Cemented carbides, mainly tungsten carbide and cobalt. This is also highly used in industrial level, and high finishing can be desired in this type. Cerments, titanium carbide and titanium nitride, titanium carbonitride with nickel and molybdenum as binders. Applications: high speed finishing and semi finishing of steel, stainless steel, cast iron. Higher speed than carbide, better finish, and it can be work for in a low feed. That means depth of cut. Coated carbide in 1970s, they improved the machinability. That's composition: titanium carbide, titanium nitride, alumina, zirconium nitride, chromium carbide, diamond. Coated thickness 2.5 to 13 millimicron. Application: cast iron steel in turning and milling operation. Best applied for high speed operation. Ceramics, synthetic diamond, and cubic bronitride. Ceramics, fine alumina powder is pressed and sintered at high pressure and temperature. Other oxide, zirconium oxide, added in the ceramics, used in finishing or hardened steels. High volt load, depth, and feed. Not for heavy interrupt cutting. Other ceramics tools, Si3N4, alumina and titanium carbide, silicon carbide. Diamond, the hardest material. It is also known as sintered polycrystalline diamond. Yeah, this type of cutting tool is high, and there is a disadvantage. It can be very expensive. High speed cutting and high finishing surface can be obtained in this type of cutting tool. And other type is cubic boron nitride. Cubic boron nitride also similar as sintered polycrystalline diamond. The application of cubic boron nitride coated tool are for machining steel, nickel-based alloys. Both sintered polycrystalline diamond and cubic boron nitride tools are expensive, as one might expect, and the application must justify the additional tooling cost. Thanks all.